In today's lesson, we're going to continue looking at continuous random variables, and in particular, we're going to introduce another two popular continuous distributions. So in the last lesson, we saw the normal distribution introduced, and today we're going to look at the exponential and the gamma distributions. Now, more specifically, the exponential is actually just a form of the gamma distribution, so really this lesson is about the gamma family distributions. And after we introduce these distributions, then we're going to move back into statistics. We're going to take all of those concepts that we've learned from probability, and we're going to start applying them to do statistics. So with that, the goals of today's lecture: to understand the exponential distribution and its properties, to understand both the relationship between the exponential distribution as well as the Poisson distribution, and to understand the gamma distribution and more particularly the specific iterations of the gamma distribution that we care about. So that's going to be the exponential distribution and another distribution known as the chi-square distribution. We'll also look at what's known as the gamma function, and that's part of the gamma distribution, and we'll see some properties that the gamma function has. So why do we need the exponential distribution or the gamma distribution? We saw with the normal distribution that we were dealing with a symmetric continuous distribution that was quite concentrated around the center, right? Remember that over 99% of the observations fall within plus and minus 3 standard deviations of the mean. Now, there's lots of processes in the real world. There's lots of data that we could observe that don't fit this at all, right? So I have up here sort of returns from stock rates or customer bounce rates or these types of things. And you can see that sort of there's this pattern in all of these charts of there being this really skewed long tail distribution, right? A lot of the values are going to be really low, but then we're going to have this really long tail where it's possible to observe something that's much greater. So not only is it not symmetric, but we have sort of a larger amount of the probability density falling in the upper tail. So anytime that we're trying to deal with a process like this, which is going to come in the forms of lots of real world processes, think about something like incomes, right? We're going to need to rely on a distribution that's not the normal distribution. So when quantities are not symmetric and instead are heavily skewed, we'll often rely on the exponential distribution. So the exponential distribution is going to be a skewed distribution, and it's a particular iteration of the gamma distribution. We characterize the exponential distribution with what's known as a rate parameter, and that rate parameter is typically denoted by lambda. And the density of it's actually quite straightforward to write down. So we take the density to be lambda times e to the negative lambda x. It's only defined for positive x, so the lowest value of x is 0, and then any positive value can be observed with an exponential distribution. We can also work out, simply by integrating here, that the expected value is going to be 1 over lambda, and that the variance is going to be 1 over lambda squared. So we see the variance is the square of the expected value. Now, sometimes you'll see people write down the exponential distribution in terms of its mean parameter instead of in terms of the rate parameter. So if you were to do that, you could call the mean mu, and then it's going to be 1 over mu anytime that you see lambda. So you might see that come up in places as well, but in this course, we'll use the rate parameter. It's a slightly more intuitive way of expressing the value here, and it makes a simpler density to write down. Unlike the normal distribution, for the exponential distribution, we can actually explicitly write down what the CDF is going to be. And again, we could get the CDF just by integrating the density there. And if you actually solve that integral, you'll find that the CDF is given by 1 minus e to the negative lambda x. Right? So it's sort of deeply related to the density there. Importantly, we're not doing 1 minus the density here, right? So there's no lambda multiplying that exponential term out front. But altogether, we can actually get the CDF in a closed form, and so you could compute those values fairly easily. We can sort of show visually what the density function looks like, and it's this idea of having sort of these long tails with lots of concentration around 0. And so we have different rate parameters here, right? And you can see that we're sort of peaking right around the 0, and then the parameters are going off to positive infinity. The different rate parameters, the higher the rate parameter, the faster the tail drops off. The lower the rate parameter, the slower it drops off. And that makes a little bit of sense, because if you think about, say, the mean of the distribution, it's going to be 1 over this rate parameter, right? And so in the case of taking lambda equals 0.5, well, then we're going to have a mean of 2. And so you need to have sort of more density up there, right? Now, the exponential distribution is quite commonly used to model processes in the real world that are counting up time. So for instance, the time till failure of a light bulb. This is maybe the most standard example that you'd see for the exponential distribution. And it can sort of have the right shape oftentimes, but there's a really important property of the exponential distribution which makes it very well suited for some problems and not particularly suited for others. The property is known as the memoryless property, or the memorylessness, right? So if we were to consider what's the probability that the exponential random variable lasts beyond some point A, given that we already know that it's lasted beyond the point B, this is going to be the same as the probability that this random variable lasts for more than the difference, right? So in other words, let's say that I want to know what's the probability that my light is going to be running for 100 hours, right? And I know that it's already been running for 50 hours. This is the same as me asking what's the probability that it's going to run for 100 minus 50 hours, or another 50 hours, right? And so it turns out that knowing that a process has been going on sort of just resets the process itself. You're not more likely to see a failure if you know that you've already been running for a certain amount of time than you would be. In sort of other words, if you want to know what's the probability that something fails within the first 10 hours, well, that's going to be the same as the probability that it fails between hours 100 and 110 if you already know that it's made it to hour 100. So essentially what we're saying is that knowing that the elapsed time of a random variable is essentially irrelevant. The process is just constantly resetting itself. It's forgetting about its past, which is why we call it memoryless. Now, in addition to this memoryless property, which can be useful for modeling certain things and very not useful for modeling other things, the exponential distribution is very closely related to the Poisson process. So when we had a rate, items occurring at a rate of alpha, so we were thinking about, say, car accidents, and they happened at some fixed rate of alpha per unit time, then we know that over an interval t, the distribution is going to be Poisson of alpha times t. If we consider how much time is elapsed between two successive events, it turns out that that's going to follow an exponential alpha distribution, right? So if we're thinking about, car accidents happen on this road at some rate, right? 1 per month or 1 per week or whatever else may happen. Once we know that, then we can also say that the time between any two car accidents is going to be distributed as an exponential distribution with the same rate parameter. Now, as I mentioned, the exponential distribution is just a specific version of gamma family distributions. So the PDF for the gamma family distributions is characterized by two different parameters. It's going to be given by both an alpha and a beta parameter. And we can see it takes on a slightly more complicated form, right? So we write it as 1 over beta to the power of alpha times by this function gamma of alpha, which we'll look at in some more detail in a moment. Then we take x to the power of alpha minus 1, e to the power of negative x divided by beta. Right? So there's a little bit more going on there, but this is sort of a generalization of the exponential distribution. We call alpha the shape parameter, and we call beta the scale parameter. Again, there will be times that you will see this distribution written out in a slightly different form, where maybe you take a different parameter to represent 1 over beta, for instance. And that will be common to see as well, but we'll use this version in the class here. We need both alpha and beta to be strictly positive, so they can't equal or be less than 0. And we find that the expected value of x is going to be alpha times beta, and that the variance of x is going to be alpha times beta squared. Okay. Now, that gamma function that we have there is defined as this integral here. So it's the integral from 0 to infinity of x to the alpha minus 1 e to the negative x. And it turns out that we can't express that in a closed form solution. That is as close to a directly computable item as we can get. And so this integral is sort of already part of the PDF there, right? But we can say a little bit more about the gamma function, and we'll take a look at that in this lesson. Before we get there, we want to just take a look at what the gamma function or the gamma distribution can look like. Okay. And so in this case, the k is going to be our alpha parameter, right? And so we can see what ends up happening as we shift around the alpha parameter. And then the theta is going to correspond to our beta parameter. Okay. And so you can see that we can get sort of all of these different variations of it. We can shift around where it looks like the mode is. We can spread out or flatten the distributions. But essentially, we're seeing sort of that exponential shape, right? We're starting as positive values, and we're going to have this long tail, and just how long the tail is and where exactly the mean is are going to be shifted around by changing our alpha and our beta parameters. Now, the gamma function cannot be expressed in a closed form analytic solution. That's what we were saying. It's only expressible as that integral. However, we do have this really nice recursive property. So if we take alpha to be larger than 1, then gamma of alpha is going to equal exactly alpha minus 1 times by gamma of alpha minus 1, right? And so if we have alpha being an integer, so take alpha equals 5, right? Then we can actually say that this must mean that the gamma of alpha is going to end up being the alpha minus 1 factorial. And if you sort of just do that recursive process, you'll see it's going to be alpha minus 1 times by alpha minus 2 times alpha minus 3, and so on, down through alpha minus 1 factorial. So for integers, we actually know exactly what the gamma function is going to look like. We also know that gamma of 0.5 is going to be the square root of pi. And this is a value that comes up quite often. It seems a little bit strange to just be arising out of nowhere, but we can show that exactly if you take gamma of 0.5, you're going to get the square root of pi. Now, if you take the integral that defines the gamma function and you stop it at x, then this is known as the lower incomplete gamma function, right? So we write it with this lowercase gamma here, and it's going to be this integral from 0 to x instead of 0 to infinity of x to the alpha minus 1 e to the negative x, right? And this notation here is mostly useful because it lets us write down the CDF of the gamma function. Right? So the CDF of the gamma function is going to be 1 over gamma, the full gamma function, times by this incomplete gamma function. And again, we're not going to so much use these in this class for lots of computation, but it's useful to know that we can take these constructs and apply them for the CDF. Again, these integrals are going to be challenging to work with, similar to the normal integrals that we were seeing in the last lesson, but you're going to be able to find sort of reference values for the incomplete gamma function or the gamma function as you need. Now, there are other distributions that also follow a gamma distribution that we're interested in. And so if you go back to how we define the gamma density, you should be able to see that if you take alpha equals 1 and beta equals 1 over lambda, then you're going to get the exponential that we saw. If we take alpha to be nu over 2 and beta to equal 2, then the resulting distribution is called a chi-square distribution, and it's going to have nu degrees of freedom. The chi-square distribution comes up often in statistics. It's going to be useful for a lot of the ways that normal distributions are also useful. We're not going to look at it a ton in this course, but it's, again, useful to know that the chi-square distribution, if you ever start hearing about it, is just a specific iteration of the gamma distribution. Now, we'll often write that if it follows a chi-squared, we'll use the actual chi-square mathematical notation here. And one of the connections that we can draw is that if we take z to be a standard normal, so normal 0, 1, then taking z square is going to give you a chi-square 1 distribution, right? So that's sort of a connection that's going to be helpful to know of. Now, that was our exponential distribution and our gamma distribution. So if we're wanting to represent skewed data, then we'll probably turn to a gamma family distribution, and specifically probably the exponential distribution. We can write down the PDF, CDF, mean and variance of the exponential distribution. And we also know that the exponential distribution has a memoryless property, and it characterizes the time between events in a Poisson process. The gamma distribution is a 2-parameter generalization, which we can write down the PDF and the CDF and the mean and the variance for, but the PDF and CDF both rely on these gamma functions or these incomplete gamma functions, which are a little bit more cumbersome to work with. We also saw that the chi-square distribution is a specific case of the gamma distribution. So with that, we sort of have all of the tools that we're going to need from probability directly. And so in the coming lessons, we're going to start taking a look more at some statistical ways of using these tools to start answering questions that we care about in statistics. So I hope to see you all in those lessons.